So today I'm going to present a paper from, actually it's not published, it's not published yet. It's going to appear maybe the next issue of the transactional graphics. It's actually, I choose this paper because actually the previous seminars I've been presenting something more about capture. This one is a bit different goal, different way. So I find it was interesting. It's actually, you can see that they managed to do a good collaboration between almost 9 people. So yeah, let's get started. Actually, the topic is always the same, like the spatial animation, because face is actually something very important. Like it's been admired for a long time, and it's indeed the face is something quite amazing. You can do this kind of faces, and so far the capture tries to somehow try to find the same pose, exactly the same pose. But this paper here is a bit different. And actually to explain this paper, the paper tried to find the different, it's a little like the difference between these two images. So you can see that the first one is actually very bad acting, kind of raw, just very exaggerated, right? But actually the human face is actually, what is more important is actually the small details. And actually these small details that usually get lost in the capture process. And not only the capture process, but it's actually why it's difficult if you want to do realistic animation. It is kind of subtle details that it's difficult to get right. It could be just the skin motion or the dynamics, how the skin is moving. But these kind of things are difficult. So also, the paper actually tried to, maybe here you cannot see very well, but it's also tried to convert some kind of low resolution mesh to some kind of high resolution. So the goals of this paper is actually thinking that when you actually do animation, it's always nice to have some editable or directable, because actually you can actually modify or adapt to the things, right? So compared to the capturing, keyframe animation can just be set to do anything or change it if you can adapt to a new situation. However, for actually when creating realistic animation, subtle changes and these things is difficult for the animator to actually get it right. So this paper somehow tries to actually tackle this problem. And then when you think about capturing, it's you capture once. When the setting is very hard, like if you want to do very high resolution, the setting is expensive and takes time. So basically you just capture once, and then once you have the capture, it's kind of hard to go back. So this is one problem, and the second part is actually many of the capture systems, actually the easy ones, are actually you lose some resolution in some way. Because you just use sparse markers, it's difficult to capture like the details, the screen, or actually because you use like blend shapes to fit some model, then you are losing expression, like you're losing the facial expression. So what this paper proposed is actually a framework to enhance some kind of low resolution animation then actually and give back these kind of subtle changes. So the paper starts from actually taking any kind of input that has some kind of low resolution. It could be like the animation, keyframe animation from one rip, or actually this kind of sparse motion track, or some kind of video-based capture, or like this kind of the Kinect-based fitting model on the depth information. So this becomes the input data to this system. So it's what they call like the directed low resolution animation. That actually we have a sequence of frames. We call this sequence A. So the idea is actually we want to actually create a database of motion that actually can help, using a data-driven approach, somehow transfer the things that are missing in these parts, right? So this database is composed by some set of expressions, for always a transition from neutral to some expression. And then it's also a set of frames that creates a very high resolution. So in comparison, this model has like less than 6,000 polygons, but this one has almost 1.5 million. So after this, using these two concepts, they propose a new concept which is called the shape space, in which actually the low resolution image is somehow projected into this space. And then based on this space, they can somehow estimate which high resolution details are missing. And then once this information is recovered, they can get actually the same input animation but in the kind of high resolution space. And like this. Okay. So the first step, of course, is preparing this space, the shape space. So first you need to have a good database, and then actually you need to encode this data into the shape space. And finally, because they want to actually deal with very high resolution, they somehow make local regions to actually speed up the process. So as I mentioned, the capture, they actually have 24 short neutral to some expression sequences, which in total makes about 1,000 frames of these kind of high resolution expressions. And then all of them has full vertex correspondence. That means that a point on like the tip of the nose, it will always be the same vertex ID. And actually, to capture this, they use the multi-view passing approach from Cabo Villa that I presented maybe 2 or 3 times ago in this seminar. So actually, after this, the idea is quite simple. You start from a frame on the database. You can low pass filter this phase, and then you get like kind of the low resolution. Then from these two, you can get the deformation gradient. So this one somehow encodes the surface details, like the difference between this and this. After that, you can have like the neutral phase of the database, which you apply the same low pass filter. And then actually you can apply the same deformation, extract the deformation gradient, and then compress it. And then you have here what is called a compressed shape space. So as you can see, this one somehow encodes like the kind of the major pose of the face, while this one just encodes the details related to this pose. So maybe the deformation gradient is not just the difference. Actually, there is a paper which is called deformation transfer that somehow proved that just the gradients was not good enough. So actually, the deformation gradient means actually considering the affine transformations that happens for every triangle. So, for example, in this case, you have a reference and a cat, so you can see actually how each triangle changes in rotation and scale, and then you can apply this to the tiger, and then optimizing this transformation. So actually, all the vertex match together. This can lead to a better transformation. So this is what makes the deformation gradient. Actually, it's a 3 by 3 metric. So the low pass frequency is actually very similar to just Laplacian smoothing. So basically, you just apply a weight based on actually, you have a vertex, you have another vertex, these have an edge in common. So you can find the cotangent weights of the adjacent faces. And then finally you somehow normalize by the area of the whole ring. So this creates this kind of smooth space. So because we have this smooth space, now actually this still 1.2 million or one very high resolution, but it's very smooth. So it means that actually we don't need to save every triangle. We just want to save actually, So what they do is actually they find some patches, like they cluster some of the faces that have very similar. And actually they say that more or less one patch has to count for 100 vertex, something like this. So it means that actually for all the triangles inside each of these clusters, they will just store one information, which is one deformation region. So this way, actually, they reduce the size of the data quite a lot. And finally, the regions. So they identify 4 regions. Actually, they compute it based on the motion of the faces in the database, but they reduce it to 4, and then they weight these areas. For example, like blue means 0 weight, and then red means 1 weight. So actually, this weight is actually helpful for separating expressions. So this way they can account for asymmetric expressions, or like, for example, like a smile and frowning. Even if there is no this local region, it means that the whole face is just one expression, right? So if you have like a closed eye expression and a smile, this is just one option. But if you have 2 regions, then it means that you can separate the smile from any of the others, so you can combine with the other. So this actually we will use a little bit later. So now now that we have the shape space encoded, now actually we have an input animation that we have, right? So as I mentioned, it could come from several sources, for example, keyframe animation. Then the first step is actually to register actually the animation with actually the database. They don't need to match perfectly. So, and then basically what the idea is, you have the input animation, you have the database, so you transfer the neutral face of the database to the input animation, and then you somehow reproduce the input animation into the high resolution model. And after that, you can find the matching within the shape space, and then you can find actually which is the interpolation of the fine details, and finally you can reconstruct the face. So more in detail, this is how it goes. So first we have here the low resolution animation. We have the neutral face of the database. So by applying non-rigid registration, we can match these 2. After that, we can somehow propagate the animation to each to the neutral face. So basically, we are reproducing the animation of the input, but this time into actually the mesh of the high resolution. And after that, we can just apply the same procedure to get the shape space. So we can get the surface detail, and then we can get actually the shape space too. So here actually we get the translation and rotation, because actually the animation can have like full head motion. So we just remove it here and store it for later for the reconstruction to keep it back. So now that we have here like the compressed shape space, so this is some examples. This is the input information, 1 frame of the input animation. Actually the transferred animation using the high resolution, and then the same with the lower frequency. So now that we have a point in the shape space, which is actually corresponding to the input animation, now the problem is actually to find actually how the different faces in this database can be combined in a linear way to actually reproduce this point. So this is quite simple. It's just actually minimizing just a linear equation. So actually, important thing is that just subject, it has to be a convex space, which means the weights have to be summed to 1, and they have to be positive. So the second part is actually, we want to introduce the concept of the regions. So it means that each region needs to be computed separately. But if it's computed separately, there might be some problems in the in-between regions. So they introduced the region weighting by actually making a least square. So we can see that actually each region can be considered as a weight per triangle, So it means each triangle has a weight. So for example, like the triangle here at the, well, this will be 1 for region 1, but it will be 0 for region 2. So it's just a 1D vector, which has each triangle has a weight. So then this can be introduced into the equation by actually this kind of list. So now that we have the weights that we compute for each region, now we want to estimate, actually, we want to interpolate the fine details. So if you remember, we stored the surface details corresponding to one point. And we have actually which shapes combined create this. So we can just create a linear combination of these small details in order to generate the final details. So in this case it's for one triangle. And actually each one of the components of the gradient, deformation gradient. So in this case it's a 3x3 matrix. So we have 9 different equations. Then for every region in that we have, then we just interpolate the different fine details based on the solved weights. And then we just make sure that all the regions are normalized, so all the weights are 1. So these actually, now that we have the fine details, it's just the only thing that rests is actually to reconstruct the surface. And actually, well, this the reconstruction of the surface is actually the same process that I presented in the last seminar, the SCA. So basically, it's actually solving a thin shell.
So is this a different paper that you presented from last time?
Yeah, but they usually use the same rendering.
Oh, is that why?
It's a different author.
Different author.
But it's kind of keep incremental.
Okay.
So actually, one paper was the capture, just based on 2 or 3 cameras. The other one was actually like the driving the kind of very high resolution. Mm-hmm. And this one is actually like the contribution is actually this kind of separation between low frequency and high frequency, and then transferring these data.
But somehow I remember this paper. This
actually, it's not.
Okay.
It's not even published. This one.
Okay.
Actually, I was checking the website and it just appeared last week.
Okay. So which one was here? This year?
Yeah, I guess so.
Okay.
So actually, it's just in the website of the author, and it says to appear in
this year
in TOG.
Okay.
So here you can see.
Okay. I remember because I reviewed this paper.
Yeah. Okay. We can stop there. Anyway, so here is the results for the rig, the manual keyframe rig. You can see that actually the result is actually a high resolution mesh with the all the details. And then same for actually just sparse data. And then here also for some kind of model fitting onto the video. And finally for this kind of Kinect. So actually in these images you can observe some of the limitation of this paper. Is actually that they assume that the low resolution animation needs to be actually curved. So the better this low resolution animation is, then actually the better the result will be. So for example, like you can see that the motion capture and the manual keyframe actually produce kind of more nice. And then the Kinect, which has like the kind of worst animation, the results are a little bit less impressive. But they say it's out of the scope of their paper. So finally, actually, they consider also not only the kind of the details, but actually the dynamics of the face. So you can see here kind of a smile in in the database. And then here you can see just a linear interpolation between just the neutral phase and the extreme pose. So you can see that actually the acceleration, it starts very fast, but finally it takes quite a lot of time to finish. So actually, for an animator, it's kind of difficult to get it right. And actually, if you don't get it right, it means you need a lot of keyframes to put them. So they provide a system to actually, just by specifying the initial position and the final position, they can somehow use the database to actually find this kind of timing. So the idea is actually basically to just extend the enhancement that they have just to time. So instead of projecting just one phase, one frame at a time, they would project the entire sequence and then match which is the best sequence in the database that match, and then somehow transfer the timings. So this is done very simple. So actually, what it means to project a sequence. So basically, it's finding a mapping, just a temporal mapping between one given input sequence and another sequence. So this temporal mapping means actually each frame of the input sequence is associated with a time in the database sequence. But this mapping needs to have a specific consideration that it needs to preserve the temporal ordering. It means that it has to be monotonically increasing. So actually, to solve this, what they do is first, each frame of the sequence is projected to each of the segments, right? So by projecting, it means like projecting to the shape space. When you project a shape in the frame in the shape space, then actually you get a combination, a linear combination of the existing faces in that database. So we are just projecting into two faces each time, a segment, right? So it means we get just a weight, like a weight between these two faces. So it means that we can actually compute the error of this projection. So this is the original frame. This is actually the weight that we computed. And then this is just a linear combination between these two. So this is an error, right? So now to solve actually the mapping, we just need to find actually the mapping that actually minimizes the whole projections over one sequence, right? So this is given that you already have like two sequences. So the only problem that finishes is actually how to find out which is the best sequence in the database. So actually there are several steps, but the basic concept is basically you just project to all of the sequence, and then you just keep track of the whole projection error. And then once you choose the sequence, then in this case you will somehow resample the sequence so that the number of samples match. It means that actually the database may have just 100 frames per sequence, but you actually want a new sequence that have maybe 500. So it means you need to first resample the two sequences so they match the same number of samples, and then repeat the process to get the new timestamps. Then you can just apply these new timestamps into the previous phase. So this shows this region. So this is the database. And actually, their new sequence, as you can see, it's just a half smile. It's not a full smile. So you can see, actually, this curve is actually the displacement of the corner of the mouth. So you can see here, you can see here at the top that the displacement is different. It's because actually it's just a half smile. But actually after the transfer, like the timings are somehow matching the same. So you can see that actually the resulting smile is quite similar. So basically this paper, it tried to somehow bridge the gap between what is a kind of the artistic way of creating animation, which is by giving some keyframes, and also like the high performance capture, and then somehow try to find like the benefits of both. So in this sense, they provide some kind of art-directable realistic animation that somehow keeps the shape, very detailed shape, and then has like the correct dynamics in a very simple way. But it's not without their limitations. So the first one is, I already mentioned, is they assume that the low frequency is actually assumed to be correct. So it means that if you just give kind of very strange animation, the result will be also very strange animation. This actually also implies that because they depend too much on the low frequency phase, it means that the actor, this method can only be applied for the same person. So they don't consider, like, the shape space only works if the input image is for the same actor. So finally, actually, they depend actually on the on the scanner, high resolution scanner. And actually the eye region is well known for being very hard to capture. So basically they cannot produce any correct eye animation. So they just, for this paper, they just choose to just close all the eyes, but actually they just decided to leave it as a manual animation. So yeah, this concludes the paper. So if you have one question.
That's my example why it cannot capture the volume of the cheek.
Because it's actually the database, it's not, how to say, they separate the problem, right? So actually the database actually is just the person just performing some expressions. So it's not doing independent, it's just the whole expression, right? So all the regions somehow interact with each other. However, in this case, actually the artist just decided to create this keyframe. So if they wanted, actually, they could put something else. And then, well, I think it's just to make the example that, just to focus on this. So, but this is because actually here, in the final keyframe, actually, there is nothing. It's just moving this area.
I have a question about the shape space. So when they generate the shape space model, I remember 100.
You mean the compression?
No. So my question is, they find the detailed mesh from this shape space. So if they, I think there is some specific rule when they make some shape space, because it can be complete each other in the similar input.
Yes, so basically the shape space is this part. So it's basically just, it means actually just one facial pose, right? Because actually this is just encoding the difference between just this kind of low resolution, like smoothed face with respect to the neutral. So it's just like the delta representation of the blend shapes. But instead of being position gradients, in this case they are actually just deformation gradients, which is actually for each vertex, sorry, for each triangle, we just store the 3x3 matrix, which encodes the difference.
If the database, some database open the mouth and close the eyes, and some database open the mouth and open the eyes, in that case, they open the mouse data is the same, but the face gradient will be different. So
yeah, okay. So you mean like you just consider the whole face as a one?
yeah.
But actually this is why the regions, they are formed. So it means that we just encode this when you solve for each region separately. So actually the extent of the solution, actually when you compute, this is actually the top equation is actually just considering the whole phase, right? So when you compute the weights here, you're right. Actually, it would create a problem because actually, if you have the eyes closed but there is a smile, but there is not this kind of phase, it will be a problem. But actually, we solve the weights just for each region. So just imagine, in a simple way, you just solve this equation 4 times. But in this case, you just consider the vertex in the red region, right? So it means that for each region, you will have different weights. So in this case, you can separate these two problems. So actually, just this more complex equation is actually to consider like the smoothing in between regions. So it's actually just putting some kind of least square solution.
Then how they prove their shape space can represent the whole input expression?
Because the results are good. This is what they say. Actually, there is no proof. Like they just say we just took 24 expressions. The results seem nice. It just means the more expressions you have. So, for example, I think the example is the kind of the dynamic warping, the time warping at the end. They didn't show any other example. So I think, for example, for the details, the spatial thing maybe is not that important actually. They have enough range, right? But maybe for the dynamic, maybe they need more they would actually need more data range. But since any data-driven approach, it's just a matter of how good is your data range, right? I think they just don't discuss that.
Yeah, I remember this paper. I think this paper got rejected twice before it finally got accepted. But then the authors never give up, and then they try to respond to the reviewers' comment like very faithfully, and eventually they got accepted.
Yeah, I think the concept is interesting, and it's different but it's been very important. Yeah, if there is no more questions.